All right, kids, good Wednesday morning. It's actually nice to be able to talk through a mask. Forget just how tiring that is. All right, so this lesson is going to have kind of two parts to it. There's going to be the thermodynamic side of it, and then there's going to be like the gas law side of it. And some of you have seen the ideal gas law in chemistry, and some of you haven't, so I'm just going to assume that you all don't know anything about the ideal gas law. So the ideal gas law is, if I can change this, hold on, PV equals Nrt. Okay, now here's the deal. If there's ever a quantity in science that has an identity crisis, it's pressure. Okay? So pressure can be in a whole bunch of different things. If you've ever checked the air pressure in your tires, that's PSI, which stands for pounds per square inch. So typically, like your car tires are inflated to about 35 PSI. Okay, that's typically where they're at. So right now, in terms of like atmospheric pressure, on every square inch of you, there's this atmosphere, which is a good thing that we have, which is pushing down on us, which is about 14 PSI. So what that means is that Hank here weighs about 14 pounds. So that means on every square inch of your body, there's an equivalent weight of Hank pushing down on your body. Now, everybody kind of think, oh, pressure only pushes down. Pressure doesn't push down. Pressure is created by all of these molecules of nitrogen, oxygen that are bouncing around, and collectively that's what's creating this pressure. So pressure just doesn't push down, because if it did, everything would just collapse. Because if pressure only pushed down like on the top of the tables, then the tables would collapse. So what's happening is that there's also an upward force, okay, created by the pressure, which is the molecules of air bouncing on the bottom side of the table as well. So it isn't just down. So you could have PSI, you could have, sometimes it's measured in atmospheres, okay? So that's typically what you use in chemistry class. So like 1 atmosphere of pressure, that's what's happening right now. That's defined as kind of like the benchmark. So typically you are under about 1 atmosphere of pressure, okay? Then you could also have kilopascals, you could have pascals, and that's what we're going to talk about in just a second. And then you can also have bars, you could have millimeters of mercury, you can have inches of mercury, okay? And that comes from how they used to measure atmospheric pressure. They would have a column sitting in a pool of liquid mercury, okay? And then literally the atmospheric pressure pushing down on this pool of mercury would push that column up. So if you've studied meteorology, you have like low pressure system and high pressure systems. So typically when we have nice weather, that's caused by high pressure. So high pressure is descending air and is pushing down on that pool of mercury, and it would make that mercury go higher in this tube. And so, oh, we have high pressure. So literally there's more pressure here, it's forcing that mercury up. If it's a low pressure system, like when we have, you know, rain or snowstorms or whatever, then there's less atmospheric pressure. And then with less atmospheric pressure, then that column drops, and oh, we're having a low pressure system. So what we're going to work on in physics is because we're on the MKS systems, meters, kilograms, seconds. What we're going to work off is what's known as pascals. So hold on, let me get your equation sheet. Give me a second. So both my honors physics and AP kids are getting this lecture today because I'm not going to redo it. So let me start with my honors physics kids. So up here on your equation sheet, up here in the top left corner, you have that 1 atmosphere is 101,300 newtons per square meter. Okay? Now, that's newtons per square meter is also known as pascals. All right? So, pascals is named after Blaise Pascal, the French physicist who came up with this weight of measurement. Now, here's what this number means, and this is relevant to all of you, okay, no matter which physics class that you're in. So, this is 101,300 newtons. So, if you consider the fact that 1 kilogram weighs about 10 newtons, okay? So, if you take this and divide this by 10, you get 10,130 of these, okay? So this is 1 kilogram mass, because each one of these weighs 10 newtons. So if you divide this by 10, you get 10,130. What that means is if you have a square meter, okay, so visualize this, you have a square meter. That's the equivalent of having 10,130 of these stacked in 1 square meter. That's how much pressure is created by this column of air that's above us, okay? But it's also pushing down on the tables as well. So it's kind of a stunning number if you think about it. Imagine 10,130 of these stacked in a square meter. That's how much pressure there is. Now, when you talk about pressure, pressure fundamentally is force per unit of area. So this is why this is in newtons per square meter. So at the end of the day, even if it's PSI, pounds per square inch, it's how many pounds there are per square inch. Well, and you'll see why this has to work out in just a second. So in a physics class, you're going to use pressure measured in newtons per square meter. If you're in a chemistry class, typically that's going to be measured in atmospheres, okay? But in a physics class, pressure is going to be in newtons per square meter or pascals. Now, here's the reason why. So if you go back to PV equaling Nrt. So for those of you that are in my AP physics class, right here on the yellow sheet, you've got 1 atmosphere of pressure here, okay, kind of right here in the middle, is 1 atmosphere, which is 1.0 times 10 to the 5th newtons per square meter, which is 1.0 times 10 to the 5th pascals. So for those of you that are in my AP physics class, that number is here. Now, this is only good to like 1 significant digit, so on this sheet, they round this thing to 1.0 times 10 to the 5th. Realistically, everybody uses like 101,300. You can also see this written, if you don't like zeros, sometimes you'll see this written as 101.3 kPa, which stands for kilopascal, so it's kind of like this radio station. Hi, welcome to 101.3 kilopascals, sending out some groovy tunes. Most of you never listen to radio anyway, so that doesn't make any sense to you. Okay. So, but here's the nuts and bolts of what we're going to do. We're going to use newtons per square meter. Okay, so let's just look at the units. So I've got a pressure here in newtons per square meter. Now, the volume is going to be in cubic meters. Okay, now look what happens here. Just look at what's going to happen here. I've got newtons per square meter times cubic meters. Those are going to cancel out, and I get Newton meters, which are the same thing as joules. So on the left side of this equation, I get joules. So if this is going to work out, this side over here also has to produce units of joules. So the N is the number of moles. Okay, so this is a flashback to chemistry. So if you remember a mole, 1 mole of anything is the relative atomic mass expressed in grams. Like for example, if you have a mole of carbon, relative atomic mass of carbon is 12.0, so that's 12 grams. If you have, magnesium, if you have a mole of magnesium, that's 24.3 grams. And they all contain Avogadro's number, which is 6.02 times 10 to the 23rd particles. Okay, so this N is going to be in moles. Now, R is what's known as the ideal gas law constant. So for those of you that are in my honors physics class, you have this R right here, which is 8.314 joules per mole Kelvin. So this R is in joules per mole Kelvin. Now, on my AP physics class, you've got, where's it at? I gotta find it. Oh, here it is. Universal gas law constant, 8.31 joules per mole Kelvin. So it's on your sheet here on this back side. Here's the conversion. On my honors physics class, I've got it all right up here at the top. Now, let's talk about temperature, okay? So, temperature is a measure of the amount of kinetic energy that a particle has, okay? So here's the classic example of how temperature is different from heat. So let's say you walk into your house and it's really cold because the furnace is broken. And you light a match, okay? Not to burn down the house, but you just light a match. So you light a match, and if you put your hand over the top of it, that's going to feel really, 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 really hot. But you're not going to heat up your house with one match. But the furnace gets fixed, and the furnace comes on, and it starts dumping out all of this air. And that air might be at like 80 degrees. So it's going to feel warm, but that's going to contain a tremendous amount of thermal energy. So when you're talking about temperature, the temperature is a measure of the kinetic energy of an individual particle. Now, you all are used to measuring temperature in Fahrenheit. Okay, so like right now it's about 72 degrees in this room. Okay, that's what you all are used to. Okay? In science, a lot of times you're going to measure stuff in Celsius. Okay, so like water freezes at 0 degrees Celsius and it boils at 100. Okay, it's an arbitrary thing that they set out. But here's the problem with Celsius and Fahrenheit. It's very easy to get negative numbers. Okay, now, or 0, that's even worse. So if you look at this equation that PV equals Nrt, here's where the Fahrenheit and Celsius turn into train wrecks. If this is 0, okay, which is easily obtained, 0 degrees Celsius, so that's the temperature that ice melts at. Well then, if this is 0, this side of the equation becomes 0, which means either the pressure goes to 0 or the volume goes to 0. Okay? Well, imagine that you're driving along and your tires are inflated and the temperature hits 0 degrees Celsius, okay, otherwise known as freezing point. Well, if it hits 0 here, and that means either your pressure or your volume is going to go to 0, so let's imagine that the pressure goes to 0. Oh, you don't have any pressure in your tires anymore. Guess what? Your tires are going to instantly deflate. So it doesn't make any sense. Worse yet, if you have a negative temperature over there. If you have a negative temperature over there, that means either you're going to have negative pressure or negative volume, which that doesn't make any sense either. So to alleviate the need for having zeros or negative numbers, we use the Kelvin scale. Now, so again, on the honors sheet, to convert to Kelvin, okay, it's up here in this little box, you take your temperature in Celsius and add it to 273. So when you get to the Kelvin scale, the beauty of the Kelvin scale is that the lowest possible temperature you can have in the Kelvin scale is 0. That's what's known as absolute 0. At that point, basically, there's something called entropy, which is the measure of disorder in the system. At 0 degrees Kelvin, that's when you lose all entropy, and basically all things stop to move. So absolute 0 is the absolute lowest temperature that you could possibly obtain. So and that's like a theoretical value. So the beauty of the Kelvin scale is that it never goes to 0 and you never have negative numbers. So this is why this temperature here has to be in Kelvin. Okay, listen to me. The temperature has to be in Kelvin. Typically, you're given a temperature in Celsius, you have to convert that into Kelvin. So on the, I'm not sure that it's on here. On for you guys that are in my AP Physics class, I don't see that conversion on here, which seems odd. Okay, you guys are just going to have to remember that you add 273 to it if you're in my AP Physics class. Okay, there you go. All right, so here's the idea that you have PV equals nRT. So let me kind of start with this. Now, typically what's going to happen is that your N and your R are going to remain constant. You're not going to change the number of moles in the system of gas, and you're not going to change R because that's the ideal gas law constant, hence the term, it's a constant, okay? So basically what you're left with is PV equals some constant times temperature. So how this typically plays out, and this should make sense, okay, if you think about this at all. So if you look at what's creating pressure, like inside a balloon, okay, and I'll do a demo with a balloon in just a second. What's creating that pressure is all these little bits of matter, oxygen and nitrogen primarily, that are bouncing around and they're hitting the sides of the wall and they're creating this pressure. So you can actually think of the ideal gas law in terms of a second grade class full of little kids named Timmy, okay? So imagine that you're in a classroom and you're going to have these little kids running around named Timmy, okay? So what's creating the pressure, okay, imagine that, God forbid, I'm teaching a second grade class, horrible as that thought would be. I'm teaching a second grade class. And what I'm measuring pressure is by the number of little kids that are hitting the sides of my legs. So imagine I'm standing here, okay, so imagine here I am, right? And I've got these little ankle biters that are running around and they're hitting the sides of my leg. So what's creating this pressure is these collisions. So the pressure is determined by two things. The number of collisions, like how many times little Timmy's ran into my leg, and also how much energy the kids have when they run into my legs. So are they just walking up and like hitting my leg and bouncing off, or are they running in full speed and hitting my leg and bouncing off? So I can either have really high energy collisions, or I can have low energy collisions. I can have a lot of high energy collisions, or I can have a small number of high energy collisions. I can have a lot of low energy collisions, or I can have a small number of low energy collisions. But my legs are going to be like the pressure sensors. Like, okay, hey, what's happening with Timmy's? What's happening in terms of the collision? Volume, that's the size of the room, okay? Now, temperature is determined by skittles, okay? So, if you raise the temperature of a gas, like let's say, for example, you take this balloon, okay, and here's this balloon, and you heat up the balloon, okay? So what's going to happen is that's like taking that room full of second graders named Timmy, and you're going to give them all a whole bunch of Skittles, all right? So they're going to have a whole bunch more Skittles, and they're going to start bouncing around because now they're really, really supercharged up on sugar, right? So if I'm the teacher and all of a sudden I sense there's this increase in pressure, I've got to figure that something has happened to the temperature. Those kids are supercharged. Now, the other thing that could happen is that I can change the volume of the room. So imagine that I'm in this room and we shrink the volume of the room. So if we shrink the volume of the room, the kids are going to be jostling around a lot more, and I'm going to be likely to have a lot more collisions. So as we go through this, I want you to think of pressure as being little Timmys running into the sides of your legs. Volume is the size of the classroom, and temperature is going to be how many Skittles that we're giving the kids. Okay? So what we're going to do is I'm going to look at what's going to happen in a vacuum. So we're going to put a balloon in a vacuum, and I'm going to show you that right now, and I'm also going to do some demos with some thermal stuff while I've got the camera stopped, and I'm going to be filming in the back of the room. So I'm going to stop this, and then I'll start it back up. So, as an example of the ideal gas law, so what I have here is a balloon, okay, and it's attached to the inside of this bell housing, and that's hooked up to a pump which is going to remove the air out from inside of here. So if you look at PV equals Nrt, right? So we're going to keep the temperature of the balloon the same. So in other words, in terms of Timmy's, we're not going to give them Skittles and we're not going to take away Skittles. So the temperature is going to stay the same. But I'm going to remove the particles that are on the outside. So what's going to happen if you look at PV equals Nrt? So I'm going to drop the pressure inside of here. So to compensate that, we're going to look at what happens to the size of the balloon. So I'm going to turn this on. And you can hear that going. Okay? So what you've observed is that the balloon has gotten bigger. So we've decreased that atmospheric pressure that was in equilibrium on the balloon. So there's less particles hitting the outside, so that allows that balloon to expand. So this is where history meets science. So in World War II, they had like the long-range bombers, typically like B-17s and B-24s, and they were open airframe, so it wasn't like a sealed airframe like when you fly today. And so, but they would fly at very high altitudes. And I don't know if you can see me, so I would kneel down. So they were flying at very, very high altitudes. And so when they were flying at very high altitudes, that decreased the pressure. So the bombing crews were not allowed to eat beans, because everybody knows what happens when you eat beans. Okay, your body generates gas, which is gas. So what would happen then is a situation like this. So when they would fly at high altitudes, that atmospheric pressure would decrease, so the gas inside of their intestines then would expand. And that became very, very, very painful because of a situation like this. So imagine that you're flying at, 30,000 feet, you're being shot at by enemy planes, and all of a sudden, the insides of your intestine are going, whoa, like this, and it's just not a good thing. So if you ever go scuba diving, you need to keep track of this, because it's the opposite that happens with scuba diving. So when you go down to lower depths, you have more and more water pushing down on top of you, and that actually increases the pressure. So if you ever do scuba diving, you need to keep this little thing in mind right here. Okay. So, I just wanted to give you that visual. Now, the other visual is going to be with thermal expansion. So let me get the gas lit here, okay? Okay, I have made fire. So, the first thing I'm going to do is this. This is like a bimetal strip. And what happens with metals is that when they get heated up, they expand, because it's kind of like little second graders with Timmy. So imagine that it's cold outside, right, and they're out there on the playground, and they're just kind of huddled together. Well, as the temperature warms up, those kids are going to start to vibrate more, and they're going to occupy more space. But different metals have different expansion rates. So what I'm going to do is I'm going to heat this up. So notice it's pretty straight right now. I'm going to heat it up. And you notice that as I heat it up, it curls. Okay? So what's happening is that the metal that's on the outside of that curve is expanding at a faster rate than the metal on the inside. So if you have like the old school the name escapes me. Thermostats, there we go. That determines like when the air conditioner or heater kicks on in your house, how that works is the strip of metal like this. So within that, if you have one that's still like a slider, then what happens is that as the temperature in your house changes, then this little piece of metal changes its deflection. As that changes that deflection, either gets hot or gets cold, that hits another piece of metal in that thermostat, that completes the circuit, and then that tells your air conditioner or heater to kick on. But then when the temperature changes, okay, in this case warms up, then that's going to curl down, it's going to lose contact with that different part, it's going to open up the circuit, and then that's going to tell the thermostat or the furnace or your air conditioning to shut off. So if you've got the old school sliding thermostat in your house, this is how it works. It's a situation like this. So here's what I want you to see. The whole point of this is that different metals expands at different rate. So the one that expands more is the one on the outside. The one that's expanding less is on the inside, because that one that's expanding more is forcing that down. Okay, so there's that. Now, the other one I've got is specifically built for this. So these are all made out of brass, and so this piece of metal right here fits exactly inside of there. Okay, it's an exact machine fit. So what I'm going to do is I'm going to heat this up, and as it heats up, it's just like giving a lot of energy to that second grade class named Kimmy. And they're gaining energy and they're going to expand, right? And they're going to get bigger and bigger, and they're going to occupy more and more space. So as I do that, now when I try and put that in there, notice that it won't fit, okay? So that piece of brass will no longer fit in here, because as that metal got hot, it expanded, and as that expanded, then it expanded so much that it will no longer fit within that. Now, if I let this thing cool down, okay, add a little bit of water, cool it back down, okay? So now, that will fit back in there, because now that temperature has dropped enough and it isn't expanding as much, and now it will fit back in there. Okay, so this is when I wish you all were here for the next part. So this is also machined to fit exactly within this gap, okay? So this will fit just in here. So what I'm going to do is I'm going to heat this up. So I'm going to heat this one up. So the question is that when this thing gets heated up, will that expansion cause that hole to get smaller, where it won't fit in there? Will it just stay the same, or will it get bigger? Okay, so those are my three options. So I'm gonna heat up this part here. Okay, I'm gonna heat up this part. So the question is that when I heat it up, will that hole get bigger? Will that hole shrink, or will it just stay the same? Okay, so that's what I want you to think about. Now, historically, most people say it's going to shrink, because that metal is going to expand, and it's going to fit, and it's going to, as it expands, it's going to make that hole get smaller. Okay, so that's typically what most people think. All right, so we're going to do this. We're going to heat it up. Get it nice and hot. So now, it actually slides in there easier, okay? So the hole actually got bigger, which is somewhat counterintuitive. So here's the best explanation, is that Mother Nature does what's easiest for Mother Nature to do. And imagine that this had been a solid piece of metal. So in other words, imagine that I could take that piece that was cut out, and I would put that piece in there. So if I put that piece in there, if I could put that back and heat it up, then that system would expand in all directions. So the same thing is happening here. So even though that metal isn't there, that metal is still trying to expand outward. And so this is why that hole got bigger. So now, even now it's cooled, it's much more difficult to make this piece go through. Whereas when it was hotter, let me heat that back up a little bit. Then, once that gets hot, that actually slides through much easier. Okay, so as things heat up, temperature changes, things get bigger, okay? In terms of length, area, and volume. All right, kids, so let me shut this down. Okay, we're back. So, if you look at what we just did with the balloon, and PV equaling Nrt. So you in the gas law, you also have like what's known as Avogadro's law, Charles' law, Boyle's law, the combined gas law, all of this weird stuff. So here's the shortcut way to do this. Typically, your N and your R are going to remain constant, okay? So if you move this temperature over here, and you get PV over temperature equals Nr. Okay? Now, so typically, unless there's a leak or you're injecting gas into the system, this remains constant. So the trick is you sit here and go, okay, well that's P1, V1, T1 equals P2, V2, T2, which sounds almost like Latin, P2, V2, Et2, okay? So here's, if you get this, you can work basically 95% of all gas law problems. So look at what we did with the balloon, okay? So we kept the temperature of the balloon the same. Okay, so T1 and T2 are the same, so I don't have to worry about those, okay? That's going to stay the same. So what you do is you cover up which variables are staying the same when comparing two different situations. So what we did with the balloon, we had P1 V1 equaling P2 V2, all right? So this was the initial set of conditions. We had some pressure within the bell chamber, and the balloon had a certain volume. So this side over here is going to be a number. I don't know what the number is, it's just going to be a number, okay? Now, but this side over here has to be the same thing. So what happened is that when I hooked it up to the vacuum pump, I still have to have the same P1, V1. So I have to have this number over here stay the same. So then, by dropping that pressure, okay, and making the pressure become a smaller value, to compensate for that, the balloon then got bigger. Oh, okay, right, P2, V2. This is my initial set of conditions. So if I drop the pressure, I'm going to increase the volume. Now, this time of year, what happens typically with your tires is a function of temperature. So if you look, because the temperature fluctuates so much, so if you look at my pen, which isn't writing today, so if you go back to P1, V1 over T1 equals P2, V2 over T2, right? So we got this going. So let's say that the volume of your tires is going to stay the same, okay? All right? The volume is going to stay the same. So I don't have to worry about that. So then I'm going to cross multiply, and I'm going to have P1 T2 equaling P2 T1. Okay, now, so notice that there's an equality sign here. So here's what happens. So you have a pressure 1, okay, and a temperature 1. So let's say that it's, 60 degrees out, okay? You got to have that in Kelvin, by the way. You always, always, always have to have these temperatures in Kelvin, okay? I cannot emphasize this enough. These temperatures have to be in Kelvin, otherwise you're going to get zeros or negative numbers, which is a train wreck. So you're going to have a certain pressure and a certain temperature, right? Now, look what happens. Cold front goes through, or it gets cold at night, and the temperature drops, Okay? So this temperature drops, it becomes smaller. We've taken Skittles away from Timmy. Okay? Timmy at this point is freaking out, going, oh my God, I have less energy because you've taken away the Skittles. So to compensate for that, the pressure has to drop as well. So imagine that I'm teaching second graders and we've removed the Skittles. The kids are running out of energy. I'm not going to feel as much pressure by the little ankle biters running into my legs because they're not going to have as much energy. Now, the other side could happen. You have P1, T1, okay, let's say that's at a cold temperature. Well, then as your tires heat up, okay, as it warms up, then as this temperature goes higher, the pressure is going to go higher because of the fact that the kids are going to have more energy. Someone gave them a bag of Skittles. They're all flipping out, running around all over the place. I have more pressure on me. So here's the beauty of this. So literally, if you go to this, okay, and set this up, right, with this P1, V1, P2, V2, that's what's going to allow you to work most problems on this. Okay, so on this assignment, and this is going to be true for both my classes, so you've got, for example, on number 7, you've got what volume is occupied by 2.2 moles of oxygen at a pressure of 2 atmospheres and a temperature of 20 degrees Celsius. So here's what you have to watch, okay? Here's what you have to watch. If you're going to use the actual PV equals nRT, and when in doubt, if you go to a default setting, okay, put those moles, this end has to be in moles, this is joules per mole Kelvin, this temperature has to be in Kelvin, this volume has to be in cubic meters, that pressure has to be in pascals, okay? So this pressure has to be in pascals, so you cannot go wrong if you convert this into pascals. Now, if you're just comparing pressures and temperatures and you're not actually using the full ideal gas law, if you're just comparing pressures at different temperatures, you can leave them in atmospheres, okay? But if you're not sure whether or not to leave it in atmospheres or not, when in doubt, convert those pressures into newtons per square meter or pascals. That's the easiest way to do this. Okay. Now, down at the bottom of this sheet, I've got these handy-dandy equations. And let me do a little bit of erasing here. And this has to do with this concept of thermal expansion. So, for some reason, this is being stupid today. Okay. So, you've got L equals L naught times 1 plus alpha delta T, and then you've got delta L equals L naught alpha delta T. Okay. So on this handy-dandy equation, thermal constant sheet, if I haven't given it to you, I'm going to send it out in an email. So what you have down here on this page, it has values of thermal expansion coefficients. Okay, that's what this alpha is. Now, this has some weird units on it. Okay, the units for alpha are Celsius to the -1. Okay, it's a weird unit, but it works. So here's the deal. The reason that that has Celsius to the -1 units is because of the fact that this is Celsius to the -1. You're going to multiply it by the change in temperature. Now, listen to me. Listen to me. This is not the temperature, okay? This is the change in temperature. So listen to me. When you're talking about a change in length, okay, you're talking about the change in temperature, not the temperature itself, okay? Listen to me. It is not the temperature. It is the change in temperature. So the bigger the change in temperature, the bigger the change in length. Now, this is L0. This is the initial length of the metal. So if you look, and these are the same, because if you go through here and you solve this and you do some rearranging, this is how you get this equation. So L0 is the initial length. So what you'll notice is that on both of these, the bigger the initial length of the metal is, the more it's going to change, okay? So this is why if you look at like bridges, okay, you have to have expansion joints for the bridges because, especially in Kansas, because Kansas undergoes these huge changes in temperature. So because that temperature changes so much, that metal, because it's a really long piece of metal to build the bridge, is going to undergo a great change in length. So that's why this is going to be this L0. So here's the cool part about this. This length, it doesn't matter what this length is in. It could be feet, it could be inches, it could be square centimeters, it doesn't make any difference. Because whatever units this is in is whatever units this is going to end up in. So if this is in meters, that's going to be in meters. If this is in inches, that's going to be in inches. Okay? It doesn't matter. Because what's going to happen here is that you're going to have alpha, which is your Celsius to the -1, multiplied by the change in temperature. So that's going to be in Celsius. That's going to be in Celsius. This has no units. So whatever length your L0 is in is whatever that new length is going to be over there. Okay? So that's the whole idea. Now also down below, so if you look on this chart, okay, so you've got like aluminum, brass, concrete, all these different values of thermal expansion. Now I want to point out one thing. If you look at ice, ice has the biggest value of thermal expansion. So this is why if you've ever like looked at ice as it's frozen, it expands greatly, because that's a whole other story, because you're forming all these hydrogen bonds which make it expand. So ice actually expands, water expands a lot when it changes into ice. So if you've ever like seen water freeze, like in a cup or something, where that water level was, once it turns into ice, that gets bigger because of the fact that it has a big thermal expansion. Now, also down here on your assignment, you've got A equals A0 times 1 plus 2 alpha delta T, and then you have volume equals V0 times 1 plus 3 alpha delta T. So the reason that we have the 2 and the 3 here is because it's dimensions. So if this is a piece of metal, let's say, and this is going to be my area naught, when I heat it up, it's going to expand in 2 dimensions. So this is why the 2 is there. If you're talking about volume and it's going to expand in 3 dimensions. That's why there's a 3 alpha here. Okay? So you've got the 3 alpha because it's volume. Now again, it doesn't make any difference what units these are in. So one of your problems, I've given you dimensions of a square in centimeters. If you just want to leave this in square centimeters, that's cool. Okay? If you want to change it into square meters, that's cool. It doesn't make any difference. Okay? Mainly because of the fact that this is going to be the same thing as this, because of the fact that this has no units over here. But here's what you have to be careful of. If the question asks for what's the change in area, so what you would have to do is calculate, you'd have the initial area, then you'd go through and calculate this, and then you'd find the new area. So if it asks for the change in area, you'd have to take this new area that you calculate here and subtract it from A0. The same thing is true of volume. This calculation here gets you the new volume. But it asks for the change in volume, you've got to take this answer and subtract that from V0. Now, play the what if game. Look at what happens on all of these. If there is no change in temperature, guess what? There is no change in length. If there's no change in temperature here, area is going to equal area naught. V is going to equal V0. So you only get changes in length, volume, or area when you have changes in temperature. And again, on all of these, the bigger the change in temperature, the bigger that change in length, or that bigger that change in volume. Okay, so at this point, I'm going to shut this down, and now I'm going to make kind of two different videos to go over the assignment, one for the honors physics and one for the AP physics. Okay, so I'm going to shut this down, and then we'll move on.